Okay, so I think let's first move on to the. Okay, just 1 second. Have to move to the page, to the right page. All right, so let's begin today's lecture. Okay. All right, so I would like to talk about number 5. Okay, first. So number 5. Now here's the question. Now suppose we have a sequence, and each term is positive. I mean, xn is positive. And so suppose the limit xn exists equal to x, and you need to show that x is greater than equal than 0. Okay, so that's the question. Is if you look at this question, you can see that it's obvious, but still we need to have a proof. Now here is the solutions, but I want to explain the solution step by step. Okay, look at the number line. So assuming that the 0 is the origin and x is the limit, and so we are using the method of contradiction. So assume that x is less than 0. And we're trying to, from there, we're trying to get a contradiction, okay? Now, actually, I did give you a hint last time. So you can see that x now on the left side of 0. So between x and 0, there's a gap. So the idea is to create an interval, a symmetric interval centered at x, which does not cover 0. So the easiest way to do this is choose the epsilon equals to the absolute value of x. That's a distance from x to 0. That's called absolute value of x. And then you intentionally, you're trying to look at that interval with that epsilon, okay? So based on the definition of convergence, we know that based on this epsilon and based on this particular epsilon, there is a k for which when n is greater than k, the distance between xn minus x is less than epsilon. I know that epsilon equal to x. Okay, so this is the one thing you can want to, obviously, this directly from the definition, we're going to have this. And from here, we're trying to get a contradiction. And you can think about it. Now, where's the xn on the graph? Xn here. It's inside the intervals. So if the xn has to be inside this epsilon interval, so xn has to be on the left side of the 0. That means xn has to be negative. But however, we know that xn is assumed to be positive. So then you can see the contradiction, right? Okay, so in order to show this contradiction, and we still need to use some argument. Okay, so once I get xn minus x is less than absolute value of x, then on the other hand, I will have another situation which will contradict to this case. Okay, and why? Because you think about this way. So here you look at on the other side, on the other hand. So okay, so now you realize that xn is positive. So this is our assumption. And also, x is negative, okay? So you look at the difference, xn minus x. Xn is positive, and minus x is also positive, right? Because x is negative. So therefore, xn minus x will become a positive number, okay? So absolute value of this number is the same as you are without absolute value. So this will equals to xn plus what? The minus x is just the absolute value of x, okay? Because x is assumed to be negative. So you can see that so the difference between xn and x now is equal to xn plus absolute value of x, okay? And so this one means that the xn, so on the last inequality, you can see that xn plus absolute value of x is greater than absolute value of x because xn is positive. So if you look at the left side and the right side, you can see that the xn minus x, the absolute value of this is greater than, okay, the absolute value of x. And that's contradict to the previous inequality. The previous inequality says the distance is less than absolute value of x. Now it's opposite. So this contradict shows that actually the initial assumption is wrong. So therefore, we must have x is non-negative. So that's the proof, all right? So from the picture, then when you argue from the other hand, you can imagine that because xn on the is positive, so on the right side of the zero. So that's why you can have this new estimate, which contradicts to the previous one. So this is our way to prove this, but this is not a unique way. It's not a unique way. The idea is, the basic idea will be the same. I mean, initially you have to create a epsilon interval surrounded at the limit x, right? So this interval does not contain the zero. So that's how you can reach the contradiction, right? Now, you can have a slightly different way to argue on the other side, because on the other hand, here presently, and at this time we are using this argument, right? But however, you can have a different argument to reach this, okay? So now I can show you the second argument. Well, the first part will be the same, but on the other hand, that later material argument will be different. All right, so in the new argument, we're still choosing epsilon equal to absolute value of x, and you are going to get the absolute value xn minus x is less than absolute value of x. So the first step is the same. Now let's look at the how to get a contradiction. I'm going to get a contradiction using a different way, okay? So what you do is you look at this first inequality, and last time we talked to you about it, the inequality with the absolute value sign, okay? The absolute value sign can be removed. Once you remove the absolute value sign, you create a two inequality, right? So if we remove the absolute value sign, you have xn minus x less than absolute value of x. So that's one thing, it's clear. But on the other side, the xn minus x has to be greater than minus absolute value of x. So after removing this inequality, the absolute value sign, you are going to have this. And this is going to help us, okay, to reach a contradiction. Now, how you're going to reach contradiction? You're going to see that here you're having two inequality, right? The left inequality, the right inequality. Now here in the sequel, I only want to use the right inequality. That's I'm only going to concentrate on xn minus x less than absolute value of x. And from there, I'm going to get a contradiction. Now, how do I do that? But here, it's very important, you have to realize that x is assumed to be negative. So if x is assumed to be negative, now you look at second inequality, you can see absolute value of x will equal to minus x because x is negative. Okay, and then you look at the left side and right side. You can see both sides contains minus x. So you can just cancel the minus x. You'll get xn less than 0. So you can see that this will also give a contradiction because this contradiction actually contradict, this inequality contradict to the assumption. Because assumption says that xn is greater than 0. Now you're getting xn is less than 0. Obviously, it's a contradiction. So you can use this way to present the contradiction. So sometimes when we handle, I mean, this is a very simple problem. Already you can see different ways. So if for more complicated problem, you may have a number of different ways to prove. Okay. So this is something you need to try to study it, because for instance, even for this problem, and you may want to think about the third method or fourth method. Okay, trying to use a creation, imagination, how you can reach a contradiction through a different argument, right? Okay, so this is the homework problem I want to discuss with you. Okay, I hope this will help you to understand more about this solution of the homework problem. Okay, next, and we are going to continue today. Okay, and so we are reached to section 2C. 2C is called the subsequences and combinations. Now here, subsequence is a very simple concept. Here we just introduce this concept, okay? But we're going to use this concept later in a later series, okay? So let's talk about subsequences. Now, what do you mean by subsequence? So suppose we have a sequence xn, okay, be a sequence in RA. And now a sequence is labeled by index, right? N is the index. N equal 1, 2, 3, 4 is labeled like that. But suppose I'm not consider the whole sequence. I just consider a part of the sequence. Let's say I'm choosing the index, a sequence of index like N1, N2, and Nk. Well, when I pick this index, we always assume that it's increasing. Okay, N1 is less than N2 and less than N3 and so on. Okay. Now this can be arbitrary numbers like N1 equal to 10, N2 equal to 15, or N3 equal to 23, and so on. And no matter what, as long as they are part of the index, they'll be fine. So with this N1, N2 to Nk to the infinity, okay, then you look at the corresponding term. Then the corresponding term is now written x nk. It's now written x nk, indicating that x nk is no longer the entire sequence anymore. It's a subsequence because the index is going from N1 to N2 to Nk. Okay, you think about some example like this. But it is very important to indicate that in this case, so xnk is a new sequence. It's different from the original sequence. It's a part of it, right? But it's more important to indicate that in the original sequence, n is the index. And in this new sequence, this is the new subsequence, okay, the k is the index. There's no n anymore because the whole index n1, n2. So the order 1, 2, 3, 4 is involved with k. It's no longer involved with n itself directly. So sometimes when we define a subsequence, we use x and k. Okay. All right. So there's a very simple theorem associated with this subsequence. Now this theorem says that suppose you have an xn sequence which converges to x. Okay, so that's the assumption. Then any subsequence of x and k also converge to x. So no matter the sign, you can have a converging sequence, no matter how you pick your subsequence, this subsequence is always a converging sequence which converge to the same limit. Now the proof of this is very simple. Okay, so let's say that x and k is a subsequence. Okay, so for first we use this assumption saying, the assumption says that xn is a converging sequence, converges to x, right? So I use the definition to write down the result. So for every epsilon, so there exists a positive k, such that if n greater than k, then epsilon value xn minus x is less than epsilon. So that's this is nothing but the definition of convergence, right? Now let's apply to the subsequence. Okay, so you see that we can pick k. So here the point is that, so look at the index of subsequence, the nk. So you see nk itself goes to infinity. So this means that nk will eventually greater than k. Okay, will eventually greater than k. So therefore, when k, the index k is large enough, k greater than k1, then nk will greater than k. There's no problems, right? So therefore, you can see that such k will always exist, and for k is greater than k1, we must have x and k minus x is less than epsilon. And that's, you can see that So this simply says that the x and k converge to the x. Okay, so this is a very basic, fundamental, but very simple result associated with subsequence. And later we're going to think about some other things, some other result. So you have to be very careful to distinguish the sequence itself and the subsequence. And they may be very different. But however, if the original sequence is a converging sequence, then all the subsequences will behave nicely. They all converge to the same number. But suppose you begin with a sequence which is the xn may not, it's not a converging sequence. Okay, suppose xn does not converge into any number. Then you look at the subsequence, you can see that these subsequences may vary. Some subsequence may be convergent to some number, and some subsequence may not converge. So the situation will become much more complicated. So we're going to have a more detailed discussion later about the subsequences. Okay. So for the section 2C, subsequence is just one thing I want to mention briefly. Is prepare ourselves for a later section. Okay. And the main things in this section is to consider combinations. Okay, so what I mean by combinations here? So let's look at so there's one big theorem we need to prove one by one. So there's a combinations of limits. What does it mean? This means that that now we are thinking about more than one sequence. So xn is a sequence, yn is another sequence, okay? And they are both convergent. So xn goes to x and yn goes to y, for instance. And then you can see that somehow from xn and y, I can combine them to make new sequences, okay? So I can, like, we can add or subtract or multiply and divide, okay? And then I'll look at those combined sequence about what you can tell the limit about the combined sequence. So that's the main things we want to talk about in this theorem. So there are the 4 parts in this result. So first, now here in the first result, we just think about one sequence, okay? So xn. And so I can, from the xn, I can create a new sequence. It's called C a constant. Okay, for any constant C, I can create a CXN. CXN itself will become a new sequence. Okay, so I'm going to show. So the first result shows that for this new sequence, the limit is just equal to C times X. Okay, so this means that the sequence XN converges to something, then CXN will converge into C times that limit. That's first result. The second result is that I can add or subtract the sequence xn and yn. And then the limit, then the new sequence will also be a converging sequence, and with the limit with the same combination. So the limit will become x plus or minus y. Okay, so if you look at the number part A and part B, you can see that if you combine these two results, you can say that actually the limit is unchanged. I mean, suppose you make any linear combination of xn and yn, the limit will follow the same combination. That's a result from A and B. Now the result, there's 2 additional parts. So result C part means product. So you multiply the sequence xn and yn, then so this means that you're multiplying the limit itself. And divides, follow the same rule. But here, where you have divide, so this means that you have to assume that y is non-zero. Otherwise, you cannot divide. Okay, so this section, basically we are focusing on these 4 results. That's called a combination of limits. And the proof of this result are extremely important because this will give you a guideline to handle some other situations. So technique involved here are very important. Okay. So today we are targeted to prove A and B, and next Tuesday we'll come back to the C and the D. Okay, A and the B. Okay, so let's look at A. Now look at, so we want to show that limit Cxn equal to Cx, okay? For instance, now here we have to look at a trivial case. Now think about constant that's here. So this result says that for any constant C, this is true, right? Okay, so we don't need to consider, we don't have to give any argument in the proof if the C if C becomes 0. So what it means is, you think about, suppose your constant C becomes 0. So 0 times the sequence, so you can see the new sequence is just the constant sequence. It's a constant sequence, everything is 0. And therefore the limit 0 times x also 0. So 0 sequence will converge to 0. Obviously this is true. There's nothing to prove, right? So therefore we may assume that C is not equal to 0. So that's a serious case we have to consider. Now, how we can prove this? So what we want to do is look at our assumption. Our assumption saying that xn goes to x. So I apply the definition of limit to this original sequence xn and see what we can do with it to get some result to the new sequence, okay? So let's pick an epsilon greater than 0, okay? So you can see that based on the definition, since limit xn equal to x, so there exists k such that if n greater than k, what do you get? We're going to get that the xn minus x absolute value is less than epsilon, right? So this standard. But for our proof, we want to make some small change. We are not only want xn minus x less than epsilon, we want this is less than epsilon divided by absolute value c. Okay, now that's the crucial point. Now, why we can do that? So originally the definition says that this is less than epsilon. Now, how can we say that this guy is less than epsilon divided by something else? The reason is because actually this epsilon can be chosen arbitrarily. So when I choose epsilon, before I use this definition to create this final inequality, I'm not thinking about epsilon itself. I'm thinking epsilon divided by c, absolute value of c. Think about that. Okay, so you use epsilon divided by square root of c, the absolute value of c, in place of epsilon in this definition. Okay, so that's why you can get this. Okay, so still we are given epsilon, then so the logic thinking is like this. For arbitrary given epsilon, now I'm thinking about epsilon divided by absolute value c, plugging this into definition. Okay, so therefore there exists n greater than k to make this happen. And this k corresponds to, not correspond to epsilon, but correspond to the epsilon divided by absolute value c. Okay, so that's the crucial step. Now, why we want to do this? And then you will understand if you look at the next step. The next step, then you look at the new sequence. Okay, the new sequence is Cxn. Okay, now you look at the Cxn minus Cx. Then you obviously this equals absolute value C times xn minus x absolute value. So this is less than C times epsilon divided by C. Now you understand why divided by C, because I have extra C for the new sequence. So once I divide the C, so C and C cancel, you can reach to the epsilon. Okay, that's the way to prove this. Okay. So by giving an opposite epsilon, you want to reach the final inequality that is less than epsilon. But to get this, I need to apply the using the definition of limit to the original sequence with epsilon divided by c, not just epsilon. This will help us to cancel the c later. Okay, so that's the proof of A, right? Any questions? Okay, no question. Let's move on to the part B. So you'll get this result, okay? Now part B is that we want to show that limit xn plus or minus yn equals x plus or minus y. So here I'm only looking at the plus case. Okay, for minus case, the proof is just similar. Okay, there's nothing new. It's these two proofs are very parallel. Okay. Okay, so we are trying to use the same kind of idea. Okay, so for any given epsilon, okay, now the assumption tells us that the limit xn equals x and the limit yn equals y. So these two things are given. And now I can apply the limit concept to these two assumptions, right? So I first look at, so we are dealing with two limits. So each limit will give you a k. So that's why I distinguish. The k1 is for the xn sequence. K2 is for the yn sequence, okay? You have two different k here. Such that when n greater than k1, absolute value of xn minus x is less than epsilon. But I don't want just this to be just less than epsilon. I want this to be less than epsilon divided by 2. So again, this is a technical reason. And for the same thing, for the y sequence, I want to do the same thing. Now again, you can do that. It's based on the same reason, because suppose epsilon is given. Now you're thinking about epsilon divided by 2, not just the epsilon. And so these k1, k2 are based on the new epsilon. That's epsilon divided by 2. So therefore, you are going to have the k1, k2 to make this happen. When n greater than k1, you will have this inequality. And when n is greater than k2, you will have the similar inequality for the y sequence. And then I can combine these two inequalities to produce the inequality I want for the combined sequence. Now, when I combine this, I want to make sure that the n, so these both inequality, like xn minus x and yn minus y, both inequality hold. Okay, so therefore, I have to pick the n is greater than k1 and also greater than k2. So naturally, I can choose n greater than maximum of k1, k2. I can actually, if you want, you can call the maximum k1, k2 to be a number k, for instance. Okay. Now, once n is greater than maximum k1, k2, you'll see we're going to have both inequality, right? And then I can come back to the work on the final inequality for the combined sequence. Okay. Now look at the combined sequence. Combined here, I still using plus minus. That's fine. So combined sequence xn plus or minus yn, right? So I need to subtract its limit, its expected limit. It's x plus or minus y. Okay. Now, if you so now you're involving 4 terms. So I put the x term together, the y term together, and then you'll have that the xn minus x is one part, and the yn, okay, yn minus y is another part. Okay, they are linked by plus or minus, depending on the previous plus or minus. Okay. But no matter what is a plus or minus, then the next step, in the next step, we use the triangle inequality. Triangle inequality is that the absolute value a plus b is less than absolute value a plus absolute value b, right? So then you can see that since xn minus x is less than epsilon divided by 2, and yn minus y is also less than epsilon divided by 2. So epsilon divided by 2 plus epsilon divided by 2 exactly equals epsilon. So if you look at from the beginning to the end, okay, for any given epsilon, now finally we see that the combined sequence will satisfy this final inequality. So that's the proof. And also you can see why we pick epsilon divided by 2. Okay, it's because eventually in the end we want exactly the epsilon. So that's the proof. Okay. Any questions? So today I want you to, so today's lecture, maybe we can close early. Today's lecture is short, basically. I don't want to consider the part C and part D. Okay, I want you to understand these A and B first. Okay, and then I want you to work on the homework problem. The homework problem is like this. So the homework problem is at the number 3. Okay, in the homework list. So suppose you have xn and yn be 2 sequences, and I want you to choose that the linear combination 2xn minus 3yn equals 2x minus 3y. So that's the homework problem, and actually the proof is very similar to this. So I choose to actually want to basically explain the entire step about this whole problem. I want you, while you're still at home, you should write down the complete proof. But also, I recommend you can think about some other example, like instead of 2xn minus 3yn, you may think about 5xn plus 6yn. You just pick an arbitrary combination, and to work from there to see how you can prove it using the same argument. So here I want to indicate how to use this technique to handle these homework problems. Okay, it's basically follow the same line, but there are some steps needs to be changed. Okay, especially the first part will be the same. Well, eventually you're going to make some change. Okay, but the key step is here in the middle. By for n greater than k1, k2, then if you look at the final inequality, because you have a new combination, right? So therefore, the final inequality will be different. Now this time is 2xn minus 3yn minus 2x minus 3y. And again, the step is to combine x turned together, y turned together. So you reach to 2 times xn minus x plus or minus. Oh, there's no plus or minus, sorry. I'm still using the previous sign here. It should be the plus the minus the 3 times yn minus x. But no matter what, no matter which sign involved here, it doesn't matter. So the next step is to use the triangle inequality. So when you use triangle inequality, you can see that there'll be 2 and 3 involved, but both 2 and 3 can be removed outside of absolute value sign. Okay, so you'll get the 2 times xn minus x plus 3 times yn minus y. Okay, and then you want to reach to epsilon. Okay, eventually you will make the epsilon to appear, but in order to do that, you can see that this time the xn minus x, if you're still using xn minus x less than epsilon divided by 2, you are not going to reach the epsilon. So you want to make xn minus x to be even smaller. You want this to be less than, like, say, epsilon divided by 4. Okay, and for yn minus y, you want to make this difference is less than epsilon divided by 6. Then you can say 2 and the 4 cancel, you'll get epsilon divided by 2. And 3 and the 6 will cancel, you'll get epsilon divided by 2. Then you add both terms, you'll exactly get epsilon. Okay, so this means that in the previous sentence, the previous part, I need to change the writing here. So for the x inequality, I want this to be xn minus x, absolute value is less than epsilon divided by 4. And for the y sequence, I want this to be less than epsilon divided by 6. Okay, then you can combine these results together. You'll see that you are going to have you can have this done. All right, any questions? And also another thing is that you can not only just it's not necessarily just involve 2 sequences. Okay, you can have 3 sequences or and as long as any arbitrary linear combination. Okay, and you'll be able to prove the similar result. No matter what, as long as it's a linear combination, the limit will also carry the same limit linear combination. Maybe a few steps for showing you. Okay, suppose you have, now think about the situation where you're involving 3 sequences. So xn plus yn plus zn. Okay, so if you look at the final inequality, you have 3 sequences involved here. Basically, it's involves 6 terms, but still you can group them like an x term together, y term together, in the third sequence, which is denoted by zn minus z together. Okay, then you use triangle inequality. Okay, you get this is controlled by xn minus x plus yn minus y plus zn minus z. You see, the triangle inequality works for more than 2 terms, not only the 2 terms. Okay, so still using the triangle inequality, you can control the combined sequence using the individual sequence, and then you can arrange the individual sequence. Let's say for each make arrangement so that for each individual sequence, so that the epsilon is epsilon divided by 3 instead of epsilon divided by 2. Now you have 3 epsilon divided by 3, so add the sum of these exactly equal to epsilon. Okay, so you can still prove the result. Okay, so there's a many different ways. I mean, can be applied many different situations, but the argument is the same. Nothing changes. Okay. Okay, I think I will stop here because this is all I have to say today. And I want you to work on the homework problem and also think about some other homework problems. I mean, similar homework problem by yourself. All right? Any questions? Okay, so no question, then we can finish early today. All right? Okay, thank you. Bye.